Welcome to lecture 5.5. Today we're going to work on solving exponential equations and logarithmic equations. This is a challenging topic, but there are simple steps, and I've got some little jokes in there to kind of remind you of what to do. Some of them are a little off color, so I'm going to apologize before we even begin. So again, we're going to solve exponential equations, and then we're going to solve logarithmic equations today. So in exponential equations, there's two types of equation. The first type we're going to look at is when they have the same base. Equations with variables in the exponents, such as 3x to the 20 and 2 raised to the power of 5x equals 64. Both of these are called exponential equations. Notice the second one in red here is actually an equation with the same base on both sides, because 64 is equal to 2 to the 6th power. So there's something called the base exponent property, and it says if we have the same base on both sides of an equation raised to a power, then the only way for this equation to be equal is if the exponents are equal. And so we're going to use this to solve exponential equations that have the same base. For example, if we have 2x plus 4 equals, 3 to the power of 2x, let me start again. 3 to the power of x plus 4 equals 3 to the power of 12. What we're going to do is simply set the exponents equal, x plus 4 equals 12, and then solve that equation, and we get x equals 8. Let's look at another example. Solve 2 to the power of 3x minus 7 equals 32. So what we're going to do first is to write each side as a power of the same number or the same base. Since 32 is equal to the power 2 raised to the power of 5, we can change the right side of the equation to 2 to the 5th power. Notice now we have the same base type exponential problem. Since the bases are the same number 2, we can use the base exponent property and set the exponents equal. Now, the way I remember this is a little DJ action or a little musical action. Drop the bass, drop the bass, drop the bass, and solve. Okay, so we're just going to drop the base out of the equation. The 2's are going to disappear, and all we're going to have left is the exponents. 3x minus 7 equals 5. This becomes an easy algebraic equation to solve. Add 7 to both sides, divide by 3, and we get x equals 4. We want to check our answer, make sure it's correct. And we do indeed get 32 equals 32. So we have a good answer. This answer is a good answer. X equals 4. We also have exponential equations with a different base. Looking at those same two expressions we had before, we can see that the expression on the left, 3 to the power of x equals 20. How do we know that? Because we can't really write 3 to a power and the power be a whole number. Like 3 times 3 is 9, times 3 is 27. We don't have any multiple or exponential of 3 that will equal 20, okay? In this case, we're going to use something called the logarithmic power property, okay? We're going to use this property to solve exponential equations by taking the log of both sides and then bringing the exponent down, okay? So let's look at one here. 3 to the power of x equals 5 squared. So what we can tell right away that we do not have a same base problem. So we're going to take a log of both sides, and we can use the common log or we can use the natural log, but we should use one of those logs because we're going to use our calculator to solve this. So if we take the log of both sides, we get the log of 3 to the power of x equals the log of 5 squared. Now we can bring down the powers on both sides, and we get x log 3 equals 2 log 5. Now, to solve this, we want to know what x equals, so we're going to divide both sides by log 3, okay? Now all we have to do is plug this into our calculator, and we get an approximate answer. The answer that you're seeing there right now is the exact answer. When we plug it into our calculator, you're going to get a long decimal, and we're going to round to so many places. In this case, 3 decimal places. And so we get x is approximately 2.93. And that really makes sense because think about it. 3 squared is 9. 3 to the power of 2 is 9. 3 to the power of 3 is 27. And since this is between 9 and 27, we would expect the exponent to be between 2 and 3. And a little bit closer to 3 because 20 is closer to 27 than it is to 9. So let's try another problem. 3 to the power of x equals 20. Again, we can see that this is not the same base. So we take the log of both sides. We bring the power down in front, so we get x log 3 equals log 20. Divide both sides by log 3. And now we have the exact answer for x. We cannot simplify this further, but we can approximate again using our calculator, and we get x is approximately 2.7268. So the solution is about 2.7268. Let's look at another example. E to the power of 0.08t equals 2500. Whenever you have an expression, an exponential expression with e in it, then we want to use the natural log, because remember, natural log uses a base e, and this will make it simpler to solve. So we're going to take the natural log of both sides. And remember, whenever you take the log of the base, remember natural log is a base e raised to a power, this just reduces to the power. For example, if we had log 10 to the power of x, that would just reduce to x because log is a common log base 10 and 10 to the power of x, they just kind of cancel out. All right. So on the left, we just have the exponent, 0.08t. And on the right, we have the log of 2500. Now we just divide both sides by 0.08, and we get our exact answer. Again, we're going to put this into our calculator and get an approximation, which is 97.8. Let's look at one that's a little more involved. It takes a little more algebraic steps, and there is sometimes some confusion. All right, again, we see we have a base 4 on one side and a base 3 on the other. So here we're going to take the log of both sides. We're going to just use the common log. There's no e in this equation, so we don't need to use the natural log, but we could. It wouldn't hurt anything. Now, the first thing we want to do after we've taken the log of both sides is bring those exponents down in front as multipliers. So the x plus 3 comes down in front of log 4, and the negative x comes down in front of log 3. It's important to put the x plus 3 in parentheses because this is now a distribution problem. This is x log 4 plus 3 log 4, and you need to make sure you're paying attention to that. If you don't, it'll look like x plus 3 log 4, and you're going to get confused and get the wrong answer. So it's important that when you have an expression in your exponent and you bring it down in front, that you then distribute the log across that whole expression. All right? Now, remember when we're solving algebraic equations, we want all terms with an x in them on one side and anything without an x on the other side. So we're going to add x log 3 to both sides, and we're going to subtract 3 log 4 from both sides. Okay, so this just effectively moves the 3 log 4 over to the other side, being negative, and the negative x log 3 coming over to this side and being positive. All right. A lot of students get stuck at this problem because they don't know what to do next. Each term has an x in it on the left side and there are no x's on the right. So that's a good setup. But they don't know how to get this x alone. Well, notice that x is in both of the terms on the left, so we can factor it out. We get x times log 4 plus log 3 in parentheses equals negative 3 log 4. Now all we have to do is divide both sides of the equations by what's in this parenthesis. And now we can solve it with our calculator. Okay, this is a really important problem for you to know how to master. It's one of the more difficult ones. So you might want to rewind a little bit and see this problem again. So we've done same base problems for exponentials. We did different base problems, and it's similar with logarithmic equations. We have two types of equations. The first type we're going to look at is when there are not all logs, okay? So here we have logarithmic equations. There's a log and an equal sign, so that makes it an equation and a logarithmic equation. But notice we have log base 2 of x equals 4. One of the terms here is not a log. The 4 is just a constant. There is no log there, and that's what I mean by not all logs. In a minute, we'll see the all log expression or equation. The second one is log of x plus 3 equals 1. And again, we have a number here. It could be a variable, it could be just x plus 3 on the right that doesn't have a log attached to it. And that's when we're going to use this not all logs method of solving. To solve this logarithmic equation, we're going to first try to obtain a single log on one side of the equation. And then we're going to write an equivalent expression in exponents. So we're going to convert that single log back to an exponential equation and solve that. So for example, here we have log base 2 of x plus log base 2 of 4 equals 4. The first thing we want to do, well, all the logs are on one side, so that's good. Now we want to make the logs on the left side into a single log. And remember, when we add two logs, this is the same as the log of their product. That's the product rule. So we can rewrite on the left side as log base 2 of 4x, and this equals 4. Now we convert it to an exponential. Once we have a single log equals a number or a variable, we convert this back to an exponent. Remember, our base is 2, our exponent is 4, and our answer is 4x. Our base was 2, our exponent was 4, and our answer is 4x. You should know how to convert between logs and exponents by now, by this section. So 2 to the power of 4 is 16. 16 equals 4x, and that just simply gives us x equals 4. Okay? So when we have logarithmic equation that doesn't have all logs, again, what we're going to do is get all the logs on one side, then make it into a single log on that one side, and then rewrite that as an equivalent exponential equation. Continuing on, let's look at another example. Here we have a very simple one, log base 3 of x equals -2. Well, there's already only a single log, so we're just going to convert this into an exponential equation. This is actually how we solved problems like this before. So we get 3 to the power of -2 equals x. This is very simple. Remember, a negative exponent means it goes to the denominator, so we get 1 over 3 squared equals x. And then, of course, 3 squared is 9, so we get x equals 1/9. It's always good to check, especially with logs, because we cannot take the log of a negative number. So we simply plug this in. And we can see that, again, we're using that same, when you take the log of the base raised to a power, the answer is just the power. So our solution is good. Let's look at one a little bit more complicated. Here we have the log of x plus the log of x plus 3 equals 1. Again, we can see we do not have all logs, not all logs, because there's a 1 there by itself with no log. We have all the logs on one side, so that's good. So now we just have to combine them into a single log. And again, we have addition, so this is the product rule. So we get the log of x times x plus 3 equals 1. Now we have a single log, we can convert it into an exponential equation. What's the base of log when there's not a base there? 10, remember. So we get x times x plus 3 equals 10 to the power of 1. Remember, this is the exponent over here when we have a log. So we get x squared plus 3x equals 10. This is a quadratic equation. We set it equal to 0 so that we can solve it. And then we can factor this into x minus 2 and x plus 5. I'm not going to go through the steps for factoring. You should know that. And so I get x equals 2 or x equals -5. Again, it's always important to check these, especially if I have multiple answers, because a lot of times one of those answers will not ring out. So we just plug this back into our original equation and see if it's true. That's why there's a question mark there instead of an equal. Is this equal to 1? Well, we get the log of 2 plus the log of 5. Well, this is the log of, remember, we can make this a single log, which is 2 times 5. The log of 2 times 5, well, that's the log of 10. Well, remember, the log of the base is always equal to 1 because this is log base 10 of 10. When the base and the answer are the same, the answer is always 1. So indeed, we do have 1 there. Now let's check when x equals negative 5. We get the log of negative 5 plus the log of negative 5 plus 3, and we're trying to see if this equals 1. Well, immediately I'm going to stop, because remember, I cannot take the log of a negative number. This is false. There is no solution to this system, so this is not a possible solution. So we only have one answer to this problem, and that is that x equals 2. Okay, the other type of equation, and this is solving logarithmic equations when there's all logs. Equations containing variables in logarithmic expressions such as log base 2 of x equals log base 2 of x plus 3. Notice that every term has a log in it. Or the second one, log of x plus the log of x plus 3 equals the log of 14. Again, log, log, log. There's logs in every single term. Terms are what we add or subtract, okay? When we have a logarithmic equation that has logs in every term, what we're going to do is get a single log on both sides and then use the property of logarithmic equality, which is similar to the idea of having the same base exponential. So for example, if we get log base a of m equals log base a of n, the only way this is going to be true is if the arguments are the same. So m has to equal n if this is the case. So we're going to use this property to solve equations. Again, once we have a log equals log, then we can just set the arguments equal to each other and solve that way. Now the way, and here's the not safe for workplace warning. The little joke I have here is that when you have log equals log, you drop a log. That's the bathroom humor. Sorry about that. And just set the arguments equal. So here we have x plus 2 equals 4, and so x has to equal 2. All right. Let's look at one that's a little more complicated. All right. Here we have the natural log of 4x plus 6 minus the log of x plus 5 equals the log of x, natural log of x. And remember that what we're trying to do here in all these cases is first get a single, when there's all logs, we first want to get a single log on both sides. So we have to convert this subtraction problem or difference into a single log. This is the quotient rule. Remember that we subtract the log of the denominator from the log of the numerator. So on the left, we have the natural log of 4x plus 6 over x plus 5 equals the natural log of x. Okay? This is the quotient rule that we learned in a previous section. Now that we have log equals log, we can use that bathroom humor and drop a log. Drop both logs, actually. Drop 2 logs here. And we get 4x plus 6 over x plus 5 equals x. If we cross multiply or multiply both sides by the denominator x plus 5, we'll get rid of the fraction. And we just get 4x plus 6 equals x squared plus 5x. Again, we can see that we have a quadratic equation. So we're going to set it equal to 0, and we get x squared plus x minus 6. If we factor this into x plus 3 and x minus 2, again, I'm not going to go through the factoring. And so we get x equals negative 3 or x equals 2. We need to plug these back in, and if you do that, you'll see that when x equals negative 3, this does not work, okay? And let's just look at that real quickly. If I plug it into the first one, I get 4 times negative 3, which is negative 12, plus 6 is negative 6, okay? It's possible that a negative number would work here. For example, if x was negative 1, it would work because 4 times negative 1 is negative 4, plus 6 is positive 2. So do not automatically think that negative values are not allowed, okay? A negative 1 wouldn't work in this equation anyway because of the right side. We'd have the natural log of negative 1. But I wanted you to see that you could have a negative 1 in that first log. So don't automatically rule out negative answers, okay? So those are the ways to solve exponential equations and logarithmic equations. Again, in exponentials, you have same base, different base, two ways to solve. And in logarithms, you have all logs and not all logs, two different ways to solve. So make sure you know all four of those methods. Reach out if you need anything, and I'll see you in the next lecture.